In this tutorial, I'm going to show you how to run a randomization test in R, specifically a test to determine whether or not there's a difference in means. The example I'm going to use is to investigate whether beer consumption increases the attractiveness of humans to malaria-carrying mosquitoes. That's discussed in the Lock 5 book as an example, as well as elsewhere, and appeared in an article on PLOS ONE that you can look at. So I've already loaded the Mosaic package, the ggplot2 package, and read in the data set. So if you haven't done so yet, you can run those 3 lines after obtaining the data set and to proceed. But let's look at what the data set looks like. And so right now you're going to see that we have a tidy data set with one column that specifies the treatment group, so either beer or water consumption, and it's counting the number of mosquitoes that were trapped in the Y-tube olfactometer for each of these trials. And what we want to do is determine whether or not we see a significant difference using a randomization test. And so just to make sure everything's okay with our data set, you could run head to see the first 6 lines of this data set appear down in your console. You could also get some basic summary statistics by running the summary and just seeing that, okay, well, we have 25 individuals in the beer group, 18 in the water group, and you can also see some information about the counts. But what we're really interested in is the difference in means between these two groups. And we're going to use some functionality found in the Mosaic package now to calculate these means by groups, just to make things even easier. And so notice how we're going to calculate the mean for each group. We're going to use the mean function, and we're going to say we want to calculate means of counts by, so tilde says by, treatment group from this data set. If we run that, what we'll see is that we get a sample mean for the beer group and a sample mean for the water group. Now we want to store the difference here, so what we could do is do this by hand, but we can actually do something a little different. So remember that we're going to use this piping syntax here, and what we're going to do is we're going to store the observed difference in means in this object called observed. So I'm storing the means. We're going to calculate each of those means as you've seen above, drop those down into this diff function, which stands for difference. So we'll run this code and then look at what observed looks like, and what we'll see is that that says water negative about 4.4. And so what difference is doing when it has 2 items here is it's going to do the second minus the first. And so that's why it's telling you which is the second, which is water here. So a negative difference here means that the beer group had more mosquitoes on average, about 4.4 more mosquitoes on average. But is that enough evidence to suggest a difference in means? Well, in order to do that, we need to understand how to simulate fake data in this situation. And so again, we're going to use a function from the Mosaic package, and that function is shuffle. Going back to the data set, you'll see why. If there's absolutely no relationship between the number of mosquitoes on an individual and whether or not they were in the beer or water group, then we should just be able to jumble the labels in the treatment column and recalculate the difference in means and treat that as an observation from what we would call the null under the null hypothesis. And that's what we're doing. In order to do this, we're going to use the shuffle function, and we're just going to shuffle treatment. So here it looks like we're just calculating a mean, which we are, but we're doing it with different group assignment because we're shuffling the treatment group. So it'll be simulated beer, simulated water groups. Running one of these, you'll see that we get a different layout here. So those are different summary statistics. Now the average for the beer group is 22.1. The water group is about 21.3. And so we could calculate the difference using the same code that we did before. So we get an observed difference of negative 2.37. Again, remembering that a negative difference means that the beer group had a larger mean than the water group. But we don't want to keep doing this over and over again. We can do it a couple times, and you'll see that you'll get different observed mean differences. But we want to be able to store these and do this relatively quickly, and that's where we're going to use something called a do loop, or do command here. And what we're going to do is we're going to amass a null distribution, so a distribution of all these differences in means under the null hypothesis that says there is no difference in means between these groups. We want to amass maybe 1,000 of these statistics, so that's what do 1000 means. And what are we going to do? Well, that will appear on the right side of the star. So do star, and then whatever's on the right side is what you're actually going to do. And what we need to do is just calculate the difference in means using the same code that we did before. And so we can run this. It'll take a couple seconds maybe, depending on your computer. And then you can look at the results. So we now have this mosquito null distribution up here. If I open it in the viewer, what you're going to see is that it's a data set with one column, and it's all of these differences in means. We have 1,000 rows for the 1,000 simulated differences of means that we've calculated. Now, in order to visualize that, I like to create a histogram, and so we can quickly recall how to make a histogram in ggplot2 and run that. Let's resize this just a tad, and you'll see that, okay, well, the difference in mean seems to be unimodal and symmetric. It's centered around 0, which makes sense because that's the truth under the null hypothesis, so it looks like things went okay. So how could we make a decision? Well, we would need to understand where our observed difference falls on this. And so I'm going to add to this code to create a histogram this geom_v line. And what that does is it's just going to plot a vertical line at the observed value on the x-axis. So that's what x-intercept equals observed means. Line type equals 2 means a dashed line. And I'm going to change the color just so it pops out a little bit. Running this, I've added the observed difference in means there. So notice it's this vertical blue dashed line. And it looks like we don't have any observed differences in sample means that are that extremely negative or more extremely negative. And so if you actually want to calculate the proportion of that, well, you would use the function prop for proportion, tilde water, so you're going to be pulling off the water column. There's only that one column in the mosquito null data set, so you're pulling off that, and then you're saying, let's look at all of the values of that statistic that are less than or equal to the observed, which is further away from 0, which is the truth under the null. Doing this, we expect to get 0, we do, and that is how you could calculate the p-value from this randomization or permutation distribution. The sign that you use here will depend on the alternative hypothesis, so you could use greater than or equal to, or you could also be looking at greater than in absolute value. We'll see those in different tutorials, but this is a crash course in how you create a randomization distribution and carry out a randomization test in R using the functionality in the Mosaic package, as well as plotting using ggplot2.